Okay, so let's talk about what a dipole moment is. We've talked about what electronegativity is, and this ties into this new concept here. So a dipole moment is a quantitative measure of the degree of charge separation in a molecule. So how separated your electronegativity values essentially are. So if you have a big difference in the electronegativities of the atoms involved inside of your, or the atoms involved in bonding, so here like hydrogen and chloride, then you'll have a large dipole moment. If you have a small difference in their electronegativities, then you'll have a smaller dipole moment. So there's these different magnitudes of pulling inside of molecules. And this is what we call a dipole moment, whenever there's that difference in pulling of your electrons. Okay, so we can determine this with our Pauling scale. And the way that we calculate this is we essentially take the difference in between your electronegativity values. So if you have something that's got hydrogen and chlorine in it, you'll find the electronegativity value on the Pauling scale of hydrogen, which was 2.2. You'll find the value of chlorine on the Pauling scale, which was, I believe, 3.16. Subtract them to find their difference. Now, this difference is going to tell us what kind of bond, what kind of sharing is going on in between these atoms. Is it equally shared, those electrons, or are they being pulled more to one side, and that's a polar bond? Or is it so strong of a pull that it's an ionic bond and that the electrons move and are entirely ripped from one of the atoms and transferred to the other? So these values right here can tell us what category it falls under. So if they are equally shared, we call this a covalent bond, equally shared. So if electrons are equally shared, it's a covalent bond. So this is what we considered nonpolar, essentially. This is nonpolar. If your electronegativity difference, which is represented in this chart by delta XP, is less than 0.4, then it's nonpolar. If your electronegativity difference is either greater than 0.4 or less than 1.7, we consider this a polar covalent bond. And this is where your electrons are unevenly shared. So one atom is hogging them more to itself than the other. And then when we get above this value, so when you're greater than this 1.7 value, then we see an ionic bond where electrons are not shared at all. Okay, not shared. They are completely transferred over to the other atom. They are not shared. So this diagram down here is kind of nice. You can see the even sharing of your electrons here. This is an electron density chart. You can see here the uneven sharing of electrons. We have our partial negative, partial positive charges. And then here's a full positive, a full negative charge, and the electrons between them are not being shared. They're entirely on one atom and not the other. Okay, so this is a pretty simple concept. If you want to calculate the difference in your electronegativity values, this is how you find the bond dipole. So if you were asked, what is the magnitude of the dipole moment in this between these two atoms, silicon and fluoride, we can simply go to our Pauling scale, locate these two. I'm going to put the larger one first, 3.98, so we can get a positive value here, and take that difference, and you're going to find this comes out right at 2.0. Okay. Oh, sorry, 1.0. 1.0. Okay. Yes, it comes out exactly at 1.0. And so this means that it falls in our range of 0.4 to 1.7, meaning that this is polar covalent. And the magnitude of the dipole moment is 1.0. So let's re-examine these really quickly so that you understand these fully. A covalent or nonpolar bond is where your electrons are shared evenly. They are split evenly between two atoms in a compound. Your polar covalent is where these are not. So you might start with your electrons in the center of your atom. Here we go. There we go. There's the energy center. And then they're going to work their way over to the more electronegative atom. So in this case, this would be a partial negative and a partial positive. You can see the electrons reside more on one side of the molecule than the other. So that's what we call polar covalent. And these have our partial positive, partial negative charges. And then our ionic is an entirely separate case where we have no sharing. So if you start with your electrons in the middle, what's going to happen for your ionic is they're going to travel to chlorine all the way over to chlorine, and that bond is going to be broken in between the atoms because the chlorine is hogging those electrons. And what you see results is that you have a full negative charge here and full positive charge over here on your ionic compounds. Okay, there we go. So that's the difference. All right, so just to reiterate, ions do not have dipole moments, as you saw in the last video. So you have a full separation of charge. That means there's no dipole moment. You can't calculate it. You can calculate the difference, but it doesn't qualify as a dipole moment, okay? These electrons are not shared. So this is what we consider a dipole. This is a full separation of charge. This is an ion. There's a difference here. So please don't get those mixed up. Okay, so you should be able to do this. So it's your turn now to give this a shot. So based on the periodic table where these different atoms fall, you should be able to rank these linear covalently bonded molecules in order of greatest dipole moment to least. And I'm going to challenge you to do that without using the Pauling scale. This should be something that you can look at it really quickly and tell the answer to. So I'm going to draw an improvised periodic table here because you will need to know their general location. So your hydrogen is up here. Let's see, we've got fluorine, chlorine, and then bromine here, and your halogens. And then up here we have oxygen, nitrogen, and carbon. So based on their location on the periodic table, you should be able to tell here which one has the greatest dipole moment. So give this your best shot. Okay, so let's take a look here at the difference in our dipole moment magnitude. So hydrogen with chlorine versus hydrogen with bromine. We need to look at the electronegativities of each of these atoms in order to determine this. So if we see chlorine and bromine on our periodic table, we can see that bromine is further down, meaning it has more electron shields, meaning it is less electronegative. So this is lower En, meaning that this is going to have a lower dipole, or a smaller dipole, sorry. And this will have a larger dipole. Because the chlorine has a higher electronegativity, hydrogen's electronegativity is obviously not changing in this compound. It remains the same. So your answer for this one would be HCl. The next one, CO2 versus N2. So if we look here, here's our carbon, here's our oxygen. There's definitely a difference here. Whereas with nitrogen, there's going to be no dipole at all, no difference. They are nonpolar. This is nonpolar. Whereas our carbon to our oxygen does have a dipole moment. However, it is pretty small, has a dipole, but we definitely know it has a bigger dipole than our nitrogen bonded to our nitrogen because there's no difference in the electronegativities here. So no En difference for this one. Okay, so the answer to this would be HCl for part A and your carbon dioxide CO2 for the next one. Okay, so try one more problem. I'm going to ask you, sorry, this was left over from last time, to calculate the magnitude of the bond dipoles for each of these compounds that you just examined. So we could tell which one was bigger than the other, but now we're going to actually put a number to quantify the difference between the bond dipoles. So you'll do that for part 1, and then for part 2, you're going to find out what kind of bonds these actually share. Is it what we call a covalent bond, Is it a polar covalent bond or an ionic bond? What can we classify these compounds as, and how are their electrons shared? Let's take a look at the answer to this problem. So we have HCl versus HBr. Let's look at the magnitude of these bond dipoles. So hydrogen's up here, and we've got Cl here. So we're going to take the difference between these values. I always like to start with the larger one so I can get a positive value and I'm not ending up with negative values at the end of the day. It really doesn't matter which one you put first because you can always take the absolute value of whatever number you get, but we do need to find the difference here. So what we end up with here is 0.96 for HCl. Let's take a look at HBr. We've got 2.96 minus 2.2. That is equal to 0.76. Now both of these are in our polar covalent area. So for A, our HCl and HBr are both polar covalent. Both polar covalent. Okay, so that means they are unevenly sharing electrons. Uneven sharing of electrons. Okay, let's take a look at our carbon dioxide. So CO2. So the bond here in between the carbon and the oxygen we're looking at is 3.44 for our oxygen minus the 2.55 for the carbon. That gives us 0.89. Let's take a look at our N2. N2 is 3.04 minus 3.04. It gives us a whopping 0. Okay, so this is also polar covalent here, and this is going to be covalent or nonpolar covalent. Covalent. And this one is polar covalent. So that's how you would answer these two problems here.